Hello, I'm Zu-Ming Jiang from Tsinghua University. I'm glad to share our work about fuzzing error handling code. Error handling code is a critical part of the program. It is used to handle various runtime errors encountered by the program and improve its reliability. But error handling code is often error-prone and hard to test because of its complexity and infrequent execution. Fuzzing is one of the most popular approaches used to detect bugs in various software. Most of the existing fuzzers are input-driven. They can generate efficient program input to cover infrequently executed code. However, some error handling codes cannot be triggered by program input. For example, the error handling code used to handle insufficient memory error. Therefore, the existing fuzzer cannot effectively test error handling code. In order to test error handling code, it is a good choice to use software fault injection, but the existing software fault injection approaches are generally context-insensitive, which may miss many bugs that can only be triggered in a specific context. The example is shown in the figure. When the runtime call stack is same as fault 1, the failure of malloc function will cause the program to exist abnormally, but no bug will be triggered. When the runtime call stack is same as fault 2, the failure of malloc function will cause double free. It is difficult for existing software fault injection approaches to find this bug. To better illustrate our work, we first classify errors into two categories. One is input-related error, which can be triggered by program input. Common functions related to such errors include string compare, string length, memory compare, etc. Another one is the occasional error, whose occurrence is occasional and has nothing to do with program input. Malloc, open, pipe are common functions related to this kind of errors. We study these two types of errors by studying 9 commonly used applications, 824 files. We find that 42% of the function calls that can trigger error handling code are related to occasional errors. Then, we study 6 state-of-the-art fuzzers and find that only 9% of the CVE submitted by them are related to occasional errors, which is far lower than 42% mentioned in the first study. This result indicates that the existing fuzzer may miss many bugs in error handling code, especially those related to occasional errors. In order to test error handling code effectively, we propose error point. In this work, we think of error size as function call that can fail and trigger error handling code. The error point is composed of error log and calling context of error site, where error log represents the location of those error sites in the program source code, and calling context represents the corresponding calling context when each error site is executed. Therefore, the error point can be represented by the following formula. Using error point, we can perform context-sensitive software fault injection. For example, when we have an error site S1 that can be executed in n different calling contexts C1 to Cn, we will record them as n different error point P1 to Pn. We can perform context-sensitive software fault injection by respectively inject faults in P1 to Pn. Based on error point, we further propose error sequence, which consists of multiple ordered error points and describe their failure situation. Each error point in the error sequence can normally run indicated as 0, or fail by injecting a fault indicated as 1. Thus, An error sequence is actually a 0-1 sequence, as shown in the following formula. Based on the context-sensitive software for injection, we propose a new fuzzing approach. This is the outline of the approach. We will first run the tested program, collect its runtime information, create an error sequence based on this information, and then mutate the error sequence. Finally, we run the tested program again and inject faults according to the error sequence. This constitutes a fuzzing loop. Here, we focus on the mutation of error sequence. At the beginning of the test, we will perform initial mutation. When the tested program runs for the first time, we will collect the executed error points and form an initial error sequence, whose all elements are 0. Then, we make one executed error point fail at each time. After that, we generate some new error sequences. In later tests, we will perform subsequent mutation. In this process, we select the error sequences that improve the code coverage and change only one executed point at each time. Then, we will generate some new error sequences, and we will drop the repeated ones. Based on this fuzzing strategy, we design a new input-driven fuzzing framework, FreeFuzz, based on context-sensitive software for injection. FreeFuzz can detect the bugs hiding deeply in the error handling code. In the evaluation, we choose 9 widely used C applications, such as Vim, ClamAV, OpenSSL. In these applications, we extract 1822 error size for context-sensitive software for injection. For each tested application, our time budget is 24 hours. For bug detection, we find 50 real bugs in 9 applications, and 32 of them have been confirmed. We find that among the 50 bugs, 39 can cause crash or DOS, 6 can cause memory corruption, 2 can cause arbitrary read, and 3 can cause memory overread. We analyze 46 bugs which are related to error handling code, and find that most of them can be triggered by one error. In addition, we also find that most of the error handling bugs are caused by improper error handling in error propagation. In order to show the effectiveness of our context-sensitive software for injection, we will place it with context-insensitive one and evaluate it. In the evaluation, we use error site to build error sequence, without considering their calling context. The evaluation results show that this method finds fewer bugs in each program than FreeFuzz, and totally only 9 bugs are found. This shows that our context-sensitive software for injection is effective in finding deep error handling bugs in different calling contexts. We also compare FreeFuzz to 4 state-of-the-art fuzzers. They are AFL, AFL Fast, AFL Smart, and FairFuzz. We selected 5 programs in Unit 2.26. In terms of code coverage, overall FreeFuzz can cover more branches because it can cover many error handling code while other fuzzers can't. In terms of bug detection, FreeFuzz can find more bugs because it can find many bugs hiding deeply in error handling code. Finally, we conclude our work. We think the existing fuzzers cannot cover error handling code effectively. In order to solve this problem, we propose a novel context-sensitive software for injection-based fuzzing strategy and design a promising fuzzing framework, namely FreeFuzz. FreeFuzz has found 50 real bugs in 9 widely used C applications and performs better than existing fuzzers. That's all for my presentation. Thank you for listening. If you have any questions, please feel free to contact us.